Thank you. Today I will be talking about parameterization of elasticity tensor, why we parameterizing elasticity tensor, and how we would be parameterizing that, and of course we are looking in the context of cryosphere. So let's look at the fate of a snowflake, where snowflake falls and comes in contact with other crystals and bonds, and these bond crystals due to sintering form granular snow, and so in a firn, this is happening over a period of time where fresh snow morphs into ice as a result of recrystallization. The snow, when it initially falls down, the orientations are random and which are isotropic, and due to recrystallization and compaction in a particular direction, gradually you see a strong crystallographic orientation. So to conclude, firn is a highly anisotropic, multi-layered old compacted snow formed as a result of recrystallization, which is found on surface of glaciers, and through gradual densification and recrystallization, firn is converted into polar ice sheets of polar ice. So we talked about what are the different kind of recrystallizations happening in firn. So there's one kind of recrystallization where you see here is which is happening in the deep firn, where the new grains are formed due to the deformation, which you see in red arrows, and the other is happening through temperature gradient metamorphism, which Wolfgang also showed. So due to vapor, you apply temperature gradient, and due to vapor transport, the grains morph into or recrystallizes into diphthos or coarsen grains, and this is also recrystallization happening in the firn. This is seen in the upper part of the shallow part of the firn, where there's exchange of air, and through exchange of air, and you could observe something like this. So we talked about anisotropy. What are the different anisotropies? One is a crystallographic anisotropy, where you see the crystals the first picture, crystals are randomly oriented, and in the next picture you see strong texture and which have a preferred crystallographic orientation, which you also see in ice. Other kind of anisotropy is coming from the structural anisotropy, where you see an isotropic structure, and here you see a transverse isotropic structure. This transverse isotropic structure is an image taken as from East Greenland, which is taken from the deep firn, where you see that the structure is transversely aligned in a particular direction. So yeah, today we would be only focusing on structural anisotropy. So why the hell are we even looking at So why are we even looking at elasticity tensor? Well, seismic waves when you transmit through the ice, they give the information of the firn structure, which is given through the reflected waves. And it is dependent on the elasticity tensor. Here you see that blue dots, where the seismic wave velocity is predicted through elasticity tensor. You see it's not so correlated. What's missing? Why it's not correlated? Let's look at, before we answer the question, let's look at the second image, where the seismic wave velocities are plotted as a function of theta, and you see that different wave velocities, you observe different wave speed of the velocities for different angles. Voila! Now, So the information missing is due to anisotropy. So we need an elasticity tensor, not just based on volume fraction, but also anisotropy, because volume fraction could give. So if you imagine if it is has high volume fraction of snow, it is harder to compress. That's why I'm talking about volume fraction. So yeah. So what are the strategies to compute the elasticity tensor? So to validate my results, one way of doing is this. I've analyzed snow microstructures of different porosities and through the different parts of the firn, which also means different anisotropic structures. I've used this images and taken in finite element simulations. And okay, that's okay. I continue. No, we stopped. Okay. I'm sorry. I found it. Okay, let's continue. So the snow microstructures are taken as an input in finite element simulations. Because I'm taking the this finite element simulation is a code provided by NIST is based on microstructure, where because it has an image, it has information of the microstructure. Obviously, if it has structural anisotropy, I get different values of elasticity tensor because the strain I'm applying in this direction is different, gives a different elasticity modulus when you apply in other direction. So yes, but you don't have a X-ray tomography in your back of your pocket to analyze your microstructures all the time, and these finite element simulations take a lot of amount of time. So we need a solution. That is parameterization, which could try to, yeah, we need a parameterization to keep it simple. Yeah. But I use these simulations anyway to validate and take this as a benchmark. So I give so much credit to finite elementation. How do they look like? That's how they look like. And you see a pink star there? That's an isotropic ice value of elasticity modulus at volume fraction 1, which basically saying that's the highest value elasticity modulus can achieve for volume fraction of 1. One thing I forgot to mention is that the volume fraction here of snow is less, and as you go gradually down, the volume fraction of snow increases, which is almost 1, which means if I'm looking at structural anisotropy, it's isotropic. So I'm not the first one to think about parameterization. There's this person who already thought about it, but this is a density-based parameterization, which says that for increasing volume fraction, there's an increase in elasticity. Doesn't make sense because the isotropic ice value is here. So you see that it's overestimating and doesn't account for anisotropy. The next parameterization is from Gisert-Kania parameterization, which is also implemented in Srivastava for snow microstructures. Other Indian guy. So this is based on volume fraction and anisotropy, but this is also based on a power law. So for these parameters, I took from the parameters obtained from his paper, so it doesn't match with my values. But anyway, you see that for isotropic at 1 is also overestimating. So we come up with Hessian-Schrittmann bounds. What are Hessian-Schrittmann bounds? Hessian-Schrittmann bounds predict the upper and lower limit of the elasticity modulus. So this is basically giving my highest point of elasticity modulus. These bounds have the information of structural anisotropy and volume fraction. And you see that it's perfectly coinciding with my isotropic ice value, and it has this limiting behavior for zero volume fraction. Of course, there's no zero volume fraction, but yeah, this is just playing around and see if things are working. But you still see an magnitude of difference from the finite element simulations and the upper limit. So, so for prolate ellipsoid structures, which are oriented in this direction, so I'm looking at C33 modulus. So if I compress in this direction, come on. So if I compress in this direction, it needs higher elasticity modulus. This you see from here. And for isotropic value, this line is coinciding with isotropic ice value too. And for structures which are aligned in this direction, the elasticity modulus is less, and you also see lower elasticity modulus. So now, since the upper bound is doing quite well, and we use finite element simulations and upper bound to come up with a parameterization, empirical parameterisation, which predicts the elasticity modulus, which goes through all the volume fractions and anisotropies. Okay, I spoke so much about structural anisotropy. How am I characterizing it? I'm characterizing through correlation lens, which gives the information of the microstructure, and the samples I'm using, the porosity varies from 0.07 to 1, which are fresh snow, snow obtained through metamorphism series, where you apply temperature gradient over a period of time and take these samples, and of course at the end of the metamorphism, as Stefan told, you end up with an anisotropic microstructure. And also from East Greenland campaign, where the snow samples are coming from the deep one, where you also see anisotropic structures. So the finite element simulations I've calculated by the code provided in my NIST. So time for results. What's happening? So here you see that I plotted elasticity modulus as a function of volume fraction. You see that for samples which are from temperature gradient metamorphism, there's a huge scatter. There's some information missing. Now I've plotted my simulations as a function of bound, which has the information of volume fraction and anisotropy, and you see the decrease in scatter and a good correlation. And if I plot simulation as a function of bound, the order of magnitude is reduced, and I used this to do an empirical fit. So time to check the performance. So this is the one from GZ-Kenya parameterization, and this is from the parameterization which I've done. So for the GZ parameterization, you see that for high density samples where the isotropy is almost 1, and the only parameter which is playing in the picture is volume fraction. Since it is a power law, you see that it is overestimating or doesn't correlate, but if you see here, it has a good correlation, and it's not based on a power law. So why it is relevant? Well, if you transmit seismic waves, you also expect a good information coming from the deep part of the firn. So I talked so much of seismic waves, and let's see in context of seismic waves, does my parameterization function? Here I plot my elasticity profile as a function of depth, where the simulations, the black line represents the simulation, and the blue line represents the parameterization proposed as a function of just volume fraction. You see that at the points it performs well, but not entirely, not consistently. And you see that the parameterization which I talked about performs well from throughout through entire depth. And next, I'm talking about the Thomson parameter. Thomson parameter gives the degree of the anisotropy. It's basically difference between C11 modulus and C33. So before looking at the results, what would you expect from anisotropic samples which are aligned in this direction? You get a negative Thomson parameter because C33 is greater than C11, which we also see for temperature metamorphism series. Initially, they are structurally isotropic, and as temperature gradient through that, gradually they transform into anisotropic samples, and this also from temperature metamorphism series. And the East Greenland samples, which are shown in the beginning, this transfer isotropic picture also exhibit negative anisotropy. Has also a negative degree of anisotropy. And as the volume fraction increases, you see the degree of structural anisotropy is almost zero. And here I'm looking at crystallographic anisotropy, which is minus 0.3, which is not so away from the structural anisotropy. So what we can say that from is that for higher porosities, that it doesn't really play a higher role if you're looking at crystallographic anisotropy or structural anisotropy. So to conclude, elastic anisotropy is important for wave propagation. So today we've looked at empirical parameterization of elasticity tensor. We looked at different anisotropies and porosities of snow microstructures, and what could be done to improve. Well, you could improve the bounds which are told by using third order correlation function, which has a complete information of your microstructure, and also an improvement could be achieved for low density samples, which doesn't really perform well. So yeah, that's it. Thank you.